Sample problems for Chemistry 111. Then we're going to talk about oxidation numbers and some stoichiometry using these redox reactions. So let's start with oxidation numbers. So let's calculate the oxidation numbers of all the elements in these two following compounds. So from our rules of oxidation numbers, right, we're going to, and the fact that the sum of oxidation numbers has to be the charge, in this case 0, we should be able to calculate or determine all the oxidation numbers for everything present. So hydrogen, oxygen, and chlorine. Right. So if we think about the rules for oxidation numbers, we have a rule for hydrogen, correct? Hydrogen is typically a +1 unless it's in a divalent or diatomic metal complex. That is not this, so this has an oxidation number of a +1. Oxygen has an oxidation number of a -2, except for when it's in a peroxide. This is not a peroxide, so it has a oxidation of -2. Right? We don't have a rule for the oxidation numbers of chlorine, so we can figure it out from everything else. Right? So we know that the oxidation number of chlorine must be the hydrogen +1 plus the oxidation number of chlorine plus the oxidation number of oxygen times the number of them that are there has to equal 0, the charge on this compound. Right? So if we take +1 plus x plus 4 times a -2 equals 0, we see that the x in this equation must be a +7. So the oxidation number for chlorine in this case is +7. We can do something very similar for the sodium thiosulfate here, the Na2S2O5. Right? Again, we're going to try to find the oxidation numbers for sodium, sulfur, and oxygen. Again, from the rules, we know that sodium, because we know it's an alkali metals always have a +1 charge and a +1 oxidation number. Oxygen, again, we talked about the rule just a second ago, but are always a -2 except in peroxides. This is not a peroxide, so it has an oxidation number of -2. The sulfur, though, we don't have a rule for, which means we, again, like chlorine above, have to figure out from what it's bound to. So this whole sum must be equal to 0. So the oxidation number of sulfur must be 2 times the oxidation number for sodium, +1, plus 2 times the oxidation number for sulfur, which we're trying to find, x, plus 5 times the oxidation number of oxygen, which is -2. That again has to equal 0. So we do this calculation for x. X then has to equal a +4. So we see that the oxidation number of sulfur in this compound is a +4. So let's look at these changes, reactions with changes in oxidation number, and do some stoichiometry with those. So we have aqueous potassium iodate and potassium iodide react in the presence of a dilute hydrochloric acid as shown in this reaction. What mass of iodine, or I2, is formed when 50 milliliters of 0.020 molar potassium iodate reacts with excess Ki and HCl, which tells us that this compound is going to be our limiting reagent, so the amount is formed is going to be determined by the amount of that is present. Right? This is an oxidation reduction reaction, but we can treat the calculations for this just like we have before. Right? So we're going to go from the volume of the solution present to the number of moles of KiO3 from the concentration. using the balanced reaction, we're now going to go to moles of I2, and then from that we want a mass, so we're going to go to grams of I2. Same sort of general stoichiometric properties we've done several times now. So the volume we have 50 milliliters, right? But this concentration is in moles per liter, so we have to convert that to liters. 1 milliliter is 1 times 10 to the negative 3 liters. And for every 1 liter of this solution, we get 0.020 moles of KiO3. So now we're left with moles of that. We want to go from the moles of the I2 from the balanced chemical reaction. For every 1 mole of KiO3, we get 3 moles of I2. Right? And we want to then end up with a mass, so we have to use the molar mass for I2. For every 1 mole of I2, it's going to have a mass of 253.8 grams. Again, as always, multiply across the top, divide across the bottom. We have, as far as significant figures go, we have 3 in this number, 2 in this number, so our final answer should have 2 significant figures, or 0.76 grams of I2. Let's look at one more. Aqueous potassium iodate and potassium iodide, again, react in the presence of dilute hydrochloric acid as shown. Again, the same reaction. What mass of I2 is formed when 15 milliliters of 0.0050 molar Ki solution reacts with 30 milliliters of 0.01 molar Ki solution in the presence of excess HCl? Right? Notice now in this one, although we're doing the same reaction, we have information about 2 of the reacting species. Right? We have a volume and a concentration, which really gives us the number of moles of both of those. So if we have information about 2 of the reactants, then this is a limiting reagent problem. Right? Which means that we're going to solve this problem twice. One, assuming that all the KiO3 is converted to I2+, and one where we convert all the Ki to I2, and then because we can only form one of those, it'll be the smallest amount. Right? So let's start with, we're going to follow the same general procedure we did last time. We're going to go from moles, or volume, to moles of I2 to grams of I2. Right? The only difference is what we start with here. We're going to do this twice, one for each kind. So let's start with this first one. That's KiO3, just like we did the last time. 15.0 milliliters of this solution that has a concentration of 0.0050 moles of KiO3 per liter of solution. Right? To get these to cancel out, we're going to need to convert. So 1 milliliter is equal to 1 times 10 to the minus 3 liters. So even though we're not doing this in order, this is, the calculation is cumulative, so it doesn't matter the order that we write these down, they still works out, the units cancel. Right. So now we have moles of KiO3. We're now going to go to moles of I2 from the balanced chemical reaction. So for every 1 mole of KiO3, we get 3 moles of I2. And just like before, for every 1 mole of I2, we have a mass of 253.8 grams. So if we converted all of this KiO3 to I2, we get a mass of 0.0571 grams. Right? But we have to do the same process for this other reactant as well. So we're going to do it the same. We'll probably do the conversion to liters the same time, or first, and then multiply. So we have 30.0 milliliters. For every 1 milliliter, we get 1 times 10 to the negative 3 liters. Multiply now by this concentration. We get 0.010 moles of Ki for every 1 liter of this solution. Now we have to do the mole-to-mole ratio from up here. For every 5 moles of Ki we react, we get 3 moles of I2. And just like above, the molar mass, 253.8 grams of I2 for every 1 mole of I2. Right. Again, if we converted all of this Ki to product, we would end up with a mass of 568 grams. But we are going to only use the smallest amount, which is going to be this number. Right? That is the smaller amount. But now we have to go back and make sure we have the correct number of significant digits. Here we had 3 for the volume, 2 for the concentration, so we need to round this number to 2 significant digits, or 0.046 grams of I2. So even though we're doing a different type of reaction, the stoichiometry still stays the same, where we're looking for the mole-to-mole ratio.